Okay. All right. All right. Good afternoon. I'm audible, right? Right. Okay. Audible. All right. So good afternoon again. We'll start. So since we finished our electric fields last week, so today we are stepping into magnetic fields, which is the last lesson you are going to learn here in this class as a theory lesson, right? This is the last lesson you are going to learn as a theory lesson, magnetic fields, right? Okay. First, I will quickly explain the importance of magnetic fields and the gravity of the lesson. Gravity of the lesson means for how many marks you are going to open up to, right? That's very important. And other than that, the other types of importance like thinking patterns, analytical skills, and other links with other lessons, right? About those things when it comes to magnetic fields, right? So put down the heading as magnetic fields. Magnetic fields. Too high. Right. Magnetic fields. Now, as a field lesson, this is the last field lesson we are learning. And this is actually the last lesson you are discussing as a batch before going to the exam, right? Last lesson, and that is magnetic fields. Okay, listen. So when it comes to magnetic fields, allocation is like this. When it comes to magnetic fields, we are usually getting around 3 to 4 MCQs, right? Usually it's around 4. It's around 4 usually. So 4 MCQs, 4 marks. Usually 4 MCQs, right? And no contribution for structure disease. I mean, no direct contribution, but sometimes magnetic field things are linked to current electricity structure disease, right? Such questions are there. Such cases are there. Otherwise, you don't have a direct experiment or direct structure disease type from magnetic fields, but usually it is linked with current electricity, right? Usually it is linked with current electricity. Then no direct contribution when it comes to essays, right? So we have a dedicated fields essay, right? You have a dedicated fields essay. Question number 8, essay number 8 in our paper, right? Dedicated essay question for fields, right? Then one essay. Now when it comes to this essay, it like changes its features among all 3 fields, and sometimes it is coming as a combination. Right? Then electric and magnetic fields are easily combined. They are very frequently combined because they are very easily linked, right? They have very much links in between, right? Even gravitational and magnetic can be linked, but popular link is between, right? Famous link is between electric and magnetic, right? Then from the essay question, 30 marks, right? 30 marks, which means 7.5 final marks, right? So it is around 11, right? Right? So usually we call this that is 11, right? But usually we call this a 10% lesson, right? With our categorization of, we have a categorization of lessons as 10% and 20% lessons when it comes to our units, no, right? Units, lessons, units will take the 10%, 20% So magnetic field is also one of the 10% lesson, right? So this is the gravity of the lesson. Right? This is the gravity of the lesson. This is the gravity of the lesson. And other important things about magnetic fields is this, right? Sometimes you might be thinking that you are not going to take magnetic field essay if the essay comes, right? But this magnetic fields lesson is not only about magnetic fields, right? This is not only about magnetic fields because, right? So one very popular opinion among students and teachers about magnetic fields is the most difficult lesson or the unit we have in our syllabus, right? That is actually true. That is actually true. The reason is that is not about the difficulty. That is not about the difficulty, not only about the difficulty. That is all about imagination. That is all about thinking parts we have here in magnetic fields, right? So undoubtedly, magnetic fields is a lesson you are going to see, you are going to learn with most number of thinking or the most number of thinking parts or the advanced thinking parts, right? So therefore, first thing, some imagination skills, some more added analytical skills, thinking skills will be needed when you learn magnetic fields, right? That is one thing. That's why most of the students are kind of scared of magnetic fields, right? They are kind of scared of magnetic fields because of these thinking parts, right? There are thinking parts, that is true, right? But when you learn the lesson from the beginning, step by step, right? When you have a good foundation, when you lay down a good foundation, right? Easily you can build up the lesson. You can build up the lesson, but that doesn't mean you don't have thinking parts. There are many thinking parts here, right? And in most of the cases, we are dealing with three-dimensional space, right? We are dealing with three-dimensional space, right? That's why imagination is required, because when it comes to a sketch or a drawing, we can have only a 2D one. We can only have a 2D diagram, a 2D drawing. But for the real scenario, real world scenario, right? We need to think of what is actually happening in the three-dimensional space, right? So that is one thing. So therefore, after learning magnetic fields, listen very carefully. After learning magnetic fields, right, your thinking side of the brain, analytical side of the brain, is definitely going to enhance, right? That is definitely going to enhance. That is the importance here of learning magnetic fields. That is not just about magnetic fields as just another lesson or just a mere lesson. No, that is not the case here in magnetic fields, right? This is going to shape up your brain, right? That's the thing. This is going to shape up your brain. Now, once you gain those skills, sometimes you might be learning those thinkings to solve a mechanics question, right? But after learning magnetic fields, with the thinking you got, with the thinking skills you got, right? You might be doing waves and oscillations question in the next essay paper, right? Or you might be doing matter and radiation, properties of matter, something else, right? The thing is, thinking is reshaped and shaping up when you do these things, applications in magnetic fields, right? So that is the most important thing that I see when it comes to magnetic fields, right? Now, as a lesson also, that is a very good lesson with very much advanced thinkings and advanced approaches, right? With everything, ultimately, you are going to increase your thinking skills, analytical skills, right? That is the most important thing about this lesson, right? ඒන්දර නිකන් හිතන්න එපා magnetic fields කරන්න ඒ නිසා මට magnetic fields ඕනේ නැහැ කියලා. එහෙම එකක් නැහැ. right? magnetic fields වල ආයෙත් ඒක කරේ නැත්නම් ඔයාලට මේ MCQs හතර තියෙනවා. right? But even though that is not just about 4 marks here, right? MCQs විතරක් කරත්, even if you do the MCQs, that is not just about 4 marks here. That is not the case, right? That is all about reshaping your brain to think of those advanced scenarios, right? So thinking එක ඔයා වෙන ඕන තරක use කරන්න පුළුවන්. That is a beauty here. That is a beauty here, right? Then with all the links that which is going to connect it to, right? If I factorize everything, right? That is not just 30. It is going to contribute around 30-35% of marks in the syllabus, right? 30-35% marks in the syllabus with all the links, right? magnetic fields වලින් ඔයාට අර හැදෙන thinking එකක් තියෙනවානේ. අන්නේ thinking එක ඔයාට use කරන්න පුළුවන් තැන් ඔක්කොම consider කරොත් 35 marks විතර ඒ thinkings වලින් එනවා, right? So therefore, as a lesson, this is very much important. This is a top notch one, right? මේක top notch lesson එකක් in terms of everything, right? In terms of everything. Okay, then we'll get into the lesson, right? We'll get into the lesson. All right. ඕක තමයි මේකේ importance එක. not just about magnetic fields. This is not only about magnetic fields. Okay. First, let's see what a magnetic field here is. First, let's see what a magnetic field here is. Right, listen. So mainly, we are discussing here about magnetism. Magnetism means, right? Magnetism means this is not just magnetized magnets, right? Magnetic magnets magnets but this is mainly about magnetism. How to make a magnet, right? How these magnetic properties are going to evolve, how these magnetic properties are going to generate, right? That is all about this magnetism. Okay, then first thing is this. Listen, first thing is now let's compare with other fields. First thing, we know gravitational fields. What was a gravitational field? Gravitational field was the field generated around a mass, right? Field generated around the mass is called gravitational field. Then electric field generated around a static charge is an electric field. When it comes to magnetic field is the field generates around a current carrying conductor, right? Very important words. Magnetic field is a field generates around a current carrying conductor, right? There should be a conductor which carries a current. Right? Around such conductors, there is a specific field generates that is called the magnetic field, right? Around current carrying conductors. Okay, first write down. And the other thing before starting, now today, since it's a starting day, my main focus is covering the main theory parts here. Right? And I'll be allocating the next day, right? Next day for the applications. I mean, today also I'll be discussing this along with applications, along with examples and example applications, right? But mainly today will be used to cover the fundamental theory concepts here, right? Today I'll be using this day mainly to cover fundamental theory concepts here, right? And then next week I'll be allocating it for all the application types. I mean, main focus will be applications in next day, and today the main focus is understanding the basic concepts. Right. First write down. The field generates around a current carrying conductor. A field generates around a current carrying conductor. Is called a magnetic field. Around a current carrying conductor is called a magnetic field. Right. So we know to graphically represent about direction and magnitude of a field, we use field lines. In gravitational fields, we had gravitational field lines. In electrostatic fields, we had electric field lines. And here we are in magnetic fields, we have magnetic field lines. Right? Okay, write down. Next heading, features of magnetic field lines. 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 Right, first one. Right, features of magnetic field lines. Features of magnetic field lines. First one. Listen. First one. First one. Magnetic field lines are always around the surface, right? Because this is the field which is around the conductor. No, this is the field which is around the current conductor, right? So that is around the surface. That is around the surface, and most importantly, the direction. Direction is from north to south because we are going to have two poles in the magnetic field as north pole and south pole, right? We call N and S, right? Always direction of field line is from N to S. Always direction is field line is from N to S, right? As we have, listen, as we have positive and negative terminals in current electricity and electric fields, right? We have north poles and south poles in a magnetic field, right? So therefore, direction of magnetic field is from N to S, right? As the first feature, write down first feature. I'm going to write this as two features. Now, when you keep this in mind, keep it in mind as direction of field line is from N to S, right? Which means that is away from N and towards S, no, right? That's the idea. First point. Magnetic field lines are magnetic field lines are magnetic field lines are acting away from N. Magnetic field lines are acting away from N. Magnetic field lines are acting away from N. Right? Second one. Magnetic field lines are acting towards 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 S. Magnetic field lines are acting towards S. Right, next one. Magnetic field lines are not intersected. Right, we had the same feature in other two fields also. Magnetic field lines are not intersected. 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 Right? Next feature. Magnetic field lines act all around the conductor. Magnetic field lines act all around. Magnetic field lines act all around a conductor. Magnetic field lines act all around a conductor. Right, and the last feature that is also very much same as what we had in other two fields, right? Closer the field lines, higher the field intensity, no, same thing, right? Last feature, closer the magnetic field lines, 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 higher the magnetic field intensity. Closer the magnetic field lines, higher the magnetic field intensity. Closer the magnetic field lines, higher the magnetic field intensity. Right? Those are the features. Right. Now, to study about any type of a field, we know we have to have field intensity. Right? In gravitational fields, we had gravitational field intensity, and in electric fields, we had electric field intensity, and here in magnetic fields, we have magnetic field intensity. That is also called magnetic flux density. Right? There are two terms here for field intensity. right? Magnetic field intensity is also called magnetic flux density, right? A similar scenario is in gravitational field. In gravitational fields, gravitational field intensity is also called gravitational acceleration, no? Something like that. Here, magnetic field intensity is also called magnetic flux density. Next heading, write down magnetic field intensity. Next heading, magnetic field intensity. Magnetic field intensity, that is also called slash magnetic flux density. Magnetic flux density, right? Denoted by capital B, denoted by capital B, denoted by capital B. Right, listen. So first thing is about the magnitude. First thing is about the magnitude of magnetic field, right? Magnitude of magnetic field intensity, right? For magnitude, we have several equations, but to prove all equations, we have a base law, right? We have a base law that is called Biot-Savart law, right? Next heading, Biot-Savart law. Biot-Savart law. The reason is this was found by two persons actually, right? Now this term is coming from the names of these two scientists, right? Biot and Savart. Biot-Savart. Biot-Savart law. Biot-Savart law. Right. Look at the board. Stop all your work and look at here. Say we have a conductor. Say we have a conductor which carries a current I. We have a conductor which carries a current I. Right. And somewhere outside the conductor, I'm going to consider a point as point X. I'm going to consider a point as point X, right? Say this angle, subtended angle is theta. So angle between these two directions is theta, right? Angle is theta. Now, listen. Say this distance is R. This is R distance away from this, away from the conductor. Now this is the current carrying conductor, right? So we know when we write very small amounts, we use delta symbol, no? Right? I have discussed about delta for small amounts under matter and radiation, right? Under matter and radiation, I discussed this idea. If you are writing very small amounts, right? This is how we write this, right? This delta. This is for considerable differences, right? This is large differences. This is very small differences. This is also delta. It's also delta, very small differences, right? Now, I'm going to consider now when these delta terms, when these delta terms are differentiated, right? You know differentiation, no? Maths can another, no? I mean, if you are doing maths, you know differentiation, right? Once these terms are differentiated, what we do is these delta terms are written as d terms, right? Then delta becomes d when we write this in a differentiation, right? That's why we had dNO dt in matter and radiation. That's why we had dNO dt in matter and radiation. Delta NO delta X, a small difference of NO, a small difference of T, right? So this d means a small difference, right? This d means a small difference, right? Now I'm going to consider a small length of this wire, dl, right? D means a small difference. D means a small difference that is coming from delta. That is coming from delta in maths, right? That is coming from delta in maths. Then this is delta L, right? Delta L. Due to this small, very small part of the conductor, right? Let's say magnetic field intensity here is B. That is also a very small one, no? That is also a very small one. Since there is a small one, this is also written as delta B in writing, when writing dB, right? Delta becomes D. Then it is written as dB. And Biot-Savart proved that this dB can be written as, listen, don't write, just look at the board. dB can be written as, or dB is proportional to, dB is proportional to IDL, IDL, right? IDL because of this small part dl, IDL sine theta over r squared, right? So this law is called Biot-Savart law. This law is called Biot-Savart law, right? This is all about magnetic flux density or magnetic field intensity at a point located r distance away, right? Due to a very small conductor of length delta L, right? Now, now take down the diagram and write this down. We are going to write this law in words after this, below this, right? मैं law clear in words. Make a law, right? First take it down. Right? This D means small difference. That's it. Right? When this D means small difference. Here also, this D means small difference. This D means small difference. A small difference. Right. After this, using this equation, we are going to prove this equation under 3 instances, right? But we don't have the proof because after this proof is an integration, mathematical integration, right? Since we can't do an integration with bio students, right? We don't do the integration part here in physics, right? We will be directly writing the integrated equations, proved equations, right? Okay, write down below in red. Write down the law in red below. Write down the law in red below. If magnetic flux density, write down the law in red. If magnetic flux density, if magnetic flux density, if magnetic flux density, if magnetic flux density at a point located, if magnetic flux density at a point located, if magnetic flux density at a point located, simple r distance away, simple r distance away, simple r distance away, r distance away from a conductor, from a conductor from a conductor of length dl, from a conductor of length dl, from a conductor of length dl, from a conductor of length dl. which carries a current capital I, 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 is dB, which carries a current capital I is dB, which carries a current capital I is dB, put a comma, which carries a current capital I is dB, put a comma, dB proportional to ideal sine theta over r square, right? This is how the law is written. Put a comma, then dB proportional to ideal sine theta over r square. That is how the law is written, right? So that is the law, Biot-Savart law, right? Now, we don't have the proof of that law and proof of the other equations also because mathematical parts are involved, right? So but you have to just know this as a law, right? Law එක දැනගෙන ඉන්න ඕනේ. Biot-Savart law. මේක තමයි law එක. Right. Now, we are going to specify this law under three different instances. Right. Listen. Listen. First instance, right? First instance. So as other field intensities, magnetic field intensity or magnetic flux density is also a vector, right? That is also a vector. Other intensities of other fields were also vectors, right? So again, with a red pen, mention that point also. Magnetic flux density is a vector, quantity. Magnetic flux density is a vector quantity. Magnetic flux density is a vector quantity. Magnetic flux density is a vector quantity. Right. First scenario, right. As row number one, write down. When a current carrying conductor, perpendicular conductor, when a current carrying perpendicular conductor spreads to a single side of considered point. Spreads to a single side of considered point. Like this. Say my considered point is x, distance is r. This should be perpendicular now. Fine. Because in A levels here, we only have these perpendicular cases. Fine. And B at this point is written as this. Now, as I told you, this result is coming after integration, mathematical integration, right? So we are directly writing this result here, right? When this changes from 0 to L, this result comes, right? Now it is coming as this, listen. And B here can be written as, now there is not delta B, there is not dB, B, total value, right? Always, there's a constant comes in magnetic fields, right? This is very much comparative to the constant we had in electric fields. In electric fields, we had 1045 epsilon naught, no? So similarly, here we have mu naught tau 45, right? I will explain what mu naught is, right? Constant is always mu naught tau 45, right? This constant is also coming, mu naught is proportionate constant or the constant of proportionality, and 45 comes after integration. That is how this term comes. And here, if there is to a single side, the equation comes as I over R. Right? Now, since we are not going to prove these equations, in physics, right? In physics, we have to keep these equations in mind. Mu naught tau 4 pi I over R. Right? And second instance, don't write. Second instance is when this is spread to both sides. Right? What happens is, don't write. what happens is, if there is to both sides of the considered point, if there is to both sides of the considered point, very comparative, these answers are very comparative, right? In that case, B is going to be always this constant comes. Constant is mu naught of O5, right? Mu naught of O5. If there is to both sides, that is 2IOR, 2IOR, right? This 4 and 2 can be cancelled, but I'm not going to cancel those two because mu naught of OY is the constant which is coming always in front of any equation you are going to write in magnetic fields, the same constant comes, right? And the third case is, don't write, third case is when this conductor subtend an angle at the considered point, when this conductor subtend an angle at the considered point like this, right? Say the subtended angle is theta by the conductor. When the conductor is curved, they are straight conductors, no? This is a curved conductor. When this distance is r, now in this case B is written as, right? B is written as mu naught of 45 I theta over r, mu naught of 45 I theta over r. So likewise, from Biot law, these three equations can be proved after integration, right? And here in physics, we'll be using these three equations, right? We'll be using these three equations as proved equations because we can't do the proof with the frame we have without integration and differentiation, right? Okay, under first one, take down only the first one. Under number one, take down the first diagram. Under number one, take down only the first diagram. Only the first diagram. Only the first diagram. Can you explain the graph again? There's no graph here, right? This is a conductor. This is a current carrying conductor, not a graph. Current carrying conductor and the considered point is r distance away from that particular point. Right? Take down only the first one. Only the first one. Right? Then as number two write down, when a perpendicular conductor, scenario 2, when a perpendicular conductor spreads to, when a perpendicular conductor spreads to, both sides of the considered point. When a perpendicular conductor spreads to both sides of the considered point. Both sides of the considered point. Right? Then take down the second scenario. Now, since we have only three scenarios in A-level questions, A-level physics questions, right? You will be finding magnetic flux density in these three scenarios only, right? Either single-sided, double-sided, or subtended angles. Right? Take down the second one. right? Then third scenario, problem number three, write down. When a curved conductor, subtends an angle theta. When a curved conductor subtends an angle theta at the considered point. When a curved conductor subtends an angle theta. When a curved conductor subtends an angle theta at the considered point. When a curved conductor subtends an angle theta at the considered point. Subtends an angle theta at the considered point. Right. Then take down the third scenario. Equations are very simple and straightforward, right? Coefficient is coming always. And if there is to a single side, I over R, right? Two sides, 2I over R, right? Angle subtended, I theta over R. Right? Understand this from these fundamental concepts properly, right? Because as I told you at the beginning, many imagination parts are going to be needed in the coming parts, right? Thinkings. Okay, now introduce all terms here. B, magnetic flux density, right? Introduce terms. I, current through conductor. B, magnetic flux density. I, current through conductor. R, perpendicular distance from conductor. R, perpendicular distance from conductor. R, perpendicular distance from conductor slash radius. Radius is applicable only for this curved scenario. Perpendicular distance from conductor slash radius, right? Then theta, subtended angle, right? We know standard unit of measuring angles is radians, no? Then it should be measured in radians, right? That is subtended angle. Should be measured in radians. Within brackets, write down within brackets. Should be measured in radians. 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 Should be measured in radians, right? Then mu naught. Listen. Mu naught is very comparative to what we had in electric field. That was epsilon naught, right? What was epsilon naught? Epsilon naught was permittivity. Permittivity determines number of electric field lines through a certain space, through a particular space. Number of electric field lines, right, through a certain space, right? This is called permeability. Very comparative. This determines number of magnetic field lines through a certain space. Permittivity and permeability, right? And mu naught is the standard value. Standard value means that is the permittivity of air or vacuum. That is the permittivity, that is the permeability of air or vacuum as epsilon naught. Epsilon naught was the standard value, right? Permittivity of air or vacuum, right? This is mu naught, permeability of air or vacuum, right? Write down mu naught, permeability. Write down permeability of air or vacuum. 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 Within brackets, write down. Within brackets, write down. Permeability determines. Within brackets, permeability determines number of magnetic field lines, number of magnetic field lines, permeability determines number of magnetic field lines, permeability determines number of magnetic field lines, through a certain space, through a certain space, through a certain space. Through a certain space. Through a certain space. Right. Now, this was all about magnitude of the magnetic field intensity or magnetic flux density. That is about the magnitude. That was all about the magnitude. Since there is a vector other than magnitude, it has a direction also. Right. Now then, let's see how this direction is written. Right. Let's see how the direction is written. Next heading. Next heading. Next heading. Next heading. Direction of magnetic field intensity. Direction of magnetic field intensity. Direction of magnetic field intensity. Direction of magnetic field intensity slash magnetic flux density slash magnetic flux density slash magnetic flux density at a point. Direction of magnetic flux density at a point. Direction of magnetic flux density at a point. Right. Listen. This is actually coming from a very popular law you already know, you are already aware about, right? You are learning about this law for the first time, for the very first time in unit 1 measurements, right? And then in rotational motion, force movements, circular motion, right? And now that is here in magnetic fields, right? That is none other than right hand law, right hand rule, right? Same thing, right hand rule. If direction of current is represented by the thumb, by the direction of thumb, right? The rest of the fingers give the direction of magnetic field, right? So that is given by right hand rule. That is given by the right hand rule. See? When direction of current is represented by the direction of thumb, right? Direction of these rest of the fingers gives us direction of magnetic field. right? That is right hand rule, not Fleming's right hand rule. That is a different one. That is also coming up. That is coming up. That is a different one. This is right hand rule, not Fleming's right hand rule. Right. First write down. Direction of magnetic flux density. Direction of magnetic flux density. Direction of magnetic flux density is given by right hand rule. 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 Right. Take this down. Right. So below this we will mention the law, mention the rule. Right. Take it down. Sorry. Okay, right. Write down the law below. Write down the law below this diagram. Write down. When direction of electric current. Write down. When direction of electric current. When direction of electric current. When direction of electric current. When direction of electric current is represented by. When direction of electric current is represented by. When direction of electric current is represented by direction of thumb. When direction of electric current is represented by direction of thumb. When direction of electric current is represented by direction of thumb. Direction of thumb. The direction of other fingers. The direction of other fingers. The direction of other fingers. Direction of other fingers gives. Direction of other fingers gives the direction of other fingers gives the direction of magnetic flux density. Direction of other fingers gives the direction of magnetic flux density. Direction of other fingers gives the direction of magnetic flux density. Right. Now let's see few examples. How do we find the direction and magnitude both? Right. First, we'll see some directions, and then I will give you some examples to see both magnitude and direction of flux intensity, right? So before moving on to that part, is there anything to clarify? Any questions? Ask quickly if there's anything. Right. Okay, it seems no questions. Right. So let's try finding some directions and see. Right. Now, when you are going to write directions, when you are going to find directions, right? Now, since this is something happening in the three-dimensional space, right? Three-dimensional space, you have to have all 6 directions. What are the 6 main directions we have? What are the 6 main directions we have in physics? Vertically upwards, vertically downwards, horizontally rightwards, horizontally leftwards, right? Then perpendicularly inwards, perpendicularly outwards. These are the directions. Right, we have discussed about these 6 directions back in rotational motion. Rotational motion වලදී මේක කරලා තියෙනවා. Right, ඒ වගේම තමයි දැන්. Right, rotational motion වලත් කරලා තියෙනවා. හරිනේ, vertical upwards, vertical downwards, horizontally rightwards, leftwards, perpendicular inwards, perpendicular outwards. Right, what directions හයම තියෙන්න පුළුවන්. Right, let's see some examples. Let's see some examples. Right, listen. First one. First one. Say this conductor carries a current in this upward direction. Say this conductor carries a current in upward direction. Right? Say this conductor carries a current in upward direction. Right? Now you are going to find direction of this magnetic flux density at these two sides. Right? Now this is how we do. Apply right hand rule here. See, apply right hand rule here. Then when the current is upwards, see, when the current is upwards, this is going to be, see, direction of here is going to be inwards. Direction here is inwards. So this side is going to be inwards. And if you check for the other side, see, rest of the fingers are coming out. So that is going to be outwards. In reality, the actual field is like this. Now, if this is the conductor, listen, this is the current carrying conductor and the current carries upwards. Right? Now, if you apply the law, see, if you apply the law right hand rule, direction is like this, see, all around. Direction is all around, like this. Direction is all around. Now, when you mark here, right, you are marking the direction at this plane, at this vertical plane only. Got it? Now, otherwise, that doesn't mean field is only at these 2 points. No, field is all around like this. Field is all around, right? If you take an aerial view, the field is like this. If you take an aerial view, right? I will show you a simulation or diagram also, right? It is 3D, it is 3-dimensional. But here, what we can mark is only the direction at the plane here, that is cross at this side, and dot at the other side, like this. Right? But if you take an aerial view like this, see, example, if you take an aerial view, say your conductor is this. Now this is your current carrying conductor, and it carries a current in this direction. Then how the conductor is placed? Conductor is placed like this, perpendicular to board, right? And the current is carried into the board, inwards. See, this is the conductor. Now if I mark the magnetic field, direction of current is cross, no? See, direction of current is cross, and direction of magnetic field is, see, clockwise. Direction of magnetic field is clockwise. Now, if I mark the magnetic field here, it is going to be clockwise like this. Got the idea? Now, in this one also, if you check it from the from above, you will see the 3D one. 3-dimensionally, that is all around, right? take this down and try this third one. Try this third one until I show you a simulation. Try this third one then. If 3 is done, you can go to 4. Okay, try 3 and 4 also. Okay, see, visible, right? So this is what is actually happening here. This is what is actually happening here, right? Now, if the conductor is carrying a current upwards, right? When you apply right hand rule, right? This is how the field is. That is all around. That is all around. Now here, what I have marked is the field on this plane only. What I have marked is a plane field on the plane only. Right? Otherwise, the field is like this. It's all around. Right? What area? But that is not on our plane. That is not on our plane. Right? something like this. See, that is not on our plane. Field is all around, right? So as you can see on the screen, and let me show you another scenario about magnets. We'll see later, right? I just need to show the direction of current when conductors are given, right? Maybe see now with the direction of current, the field changes, right? With the direction of current, this is how the field changes, right? Here also, see, same thing, same thing. When the current carries by the conductor in upwards or downwards or whatever the direction it is, right? The field generated all around the conductor according to right hand rule, right? That always follows the right hand rule. That always follows the right hand rule, right? Maybe there are no animations here, but you can see, right? So that is how it happens. See, see. So when current flows in this direction, magnetic field is in this direction. Apply right hand rule and see. Current flows in rightward, kind of horizontal rightward direction. Right? So magnetic field is around this. Right? Now with the simulation, I think it's clear enough. Right? So again, in the coming parts also, since they are 3D, right? Everything is three-dimensional here. Right? Everything is in the three-dimensional space. Right? And in the coming parts also, I will show you what is happening three-dimensionally. I will show you what is happening here three-dimensionally. Right? And using that, imagine what's happening here. That's why I told you this is about imagination. That is about imagination, right? Then you should be able to imagine what's happening here. Looking at this one, looking at the diagram. Give me 1 second. Okay, right. Then what about this? Current is carried in rightward direction. Then apply this, right? This side is cross. This side is cross. Right? Field is around. Then 3D එක අඳින්න පුළුවන් ඕන නම් it is like this. Right? It is like this. It is like this. What I need is the field at this plane. On the plane, that is cross. Then on the plane, this is cross. Right? Then on the other plane, that is dot. Got it? So that's why we don't mark this way. Right? This diagram is not that clear enough when the circle is marked. Otherwise, in reality, that acts as a circle. Three-dimensional space. Right here, current is outwards. If the current is outwards, see, direction of field is anti-clockwise. Direction of field is anti-clockwise. B. Like this. Right? Let's see another example. What about this one? Try this one. Try this. And now ask if any questions you got, right? Again the same thing. See, again the same thing. Direction of current is downwards. Then thumb is downwards. Right? Apply the thumb downwards. And always make sure that when you apply hand rules, right? In force movements, rotational motion, also I have told you, right? When you apply hand rules, make sure your hand or the palm and the diagram you apply is on the same plane. Right? Otherwise, having the diagram here, don't apply the rule somewhere else like this. Right? If your diagram is on the board, right? Put your palm on the board, then apply. Right? Is downwards, then this side is cross. This side is cross. This is dot. Right? Like this. Then what about this? A curved conductor. And I need field here. I need the field here at this point. Right? Right. Listen. Another small tip. Another small tip. If a curved conductor is given, right? If a curved conductor is given, right? Even if you switch these two, doesn't matter because they are always two perpendicular directions, no? Right? Always thumb to the other fingers are perpendicular. Then even if you switch these two, doesn't matter. Now, when a curved conductor is given, it is much easier when you switch these sides. Right? Now, the current is in this direction. See? Now, when you apply, see, current is in this direction. Current is upwards, like this. Current is upwards, right? Current is upwards. So, apply current is upwards, right? Upwards. Then this is going to be cross at this point. At this point, cross. At this point, cross. Right? Likewise, first thing is you can find the direction, right? That is about the direction. And now let's see how to write the magnitude. Magnitude then direction. Direction magnitude. Right. I can give you a minute. You can ask if anything about writing direction. Right. Ask if any questions about writing direction. I can give you a minute to check what we have done so far here and ask questions. Raise your hand if it is clear enough up to here. Raise your hand if it is clear enough. Right. So understand these concepts from the beginning. Right. So as I told you, thinkings are there, imaginations are there, but understand from the beginning. Then It won't be that much difficult. 6-1. In 6-1, if a curved one is given, switch these two, right? Switch these two. That is also fine. That is also fine, right? Say your conductor is like this, then by switching these directions, apply it like this. Otherwise, you can't apply the thumb in a curved direction, no? Then switch these two and apply like this. Then it is going to be cross, right? What else? Anything else? Anything else? No, right? Okay, then let's move on. Okay, then write down, write down as a question, write down as a question, write down as a question, write down. Determine, 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 determine direction and magnitude. Determine direction and magnitude. Determine direction and magnitude. Determine direction and magnitude of magnetic flux density, of magnetic flux density, direction and magnitude of magnetic flux density at point x, at point x, at point x. At point x. In the scenarios given below, at point x in the scenarios, at point x in the scenarios given below, at point x in the scenarios given below, point x in the scenarios given below. Okay. First one. First one. Right. So in each scenario, I'll be marking a point as x. Right. In each scenario, I'll be marking a point as x. Right. And this is the direction of current through this conductor. And distance from here to this point is, say, r. Right. Now, we are going to write the magnetic field intensity or magnetic flux density at point x due to this wire, due to this wire. Right. Listen, I'm going to explain the first one. Listen, listen. Now, when writing magnetic flux density, we have only three scenarios, no? Right? If the conductor is to one side of the considered point, right? Second one, if the conductor is to both sides from the considered point, or if it subtends an angle. Then all the questions you see here, right, will have those three scenarios. Right? Then we have to simplify it accordingly. Write the direction and magnitude accordingly and simplify it accordingly. Right? So first, let's see the direction here at x. Direction at x. Listen. First thing is this conductor, this one, horizontal conductor. Horizontal conductor goes through considered point, no? Horizontal conductor goes through considered point. R of the equation was perpendicular distance. Right? R of the equation was perpendicular distance. This goes through the considered point. When it goes through considered point, there is no perpendicular distance for this horizontal conductor. No perpendicular distance from the conductor to the considered point. Then there won't be any contribution. There won't be any contribution from this conductor. There won't be any contribution from this conductor. But from the other one, there is a perpendicular distance r. From the other one, there is a non-zero perpendicular distance, that is r. That is r. Right? So due to this one, I'm going to check the direction at this side. Downwards, no? That is dot. Then direction at the magnetic field here is going to be, direction of the magnetic field here at x is going to be dot. Right? And now we can write the magnitude. Now we can write the magnitude. Then B is given by mu naught tau 45, mu naught tau 45. Right? Now this field is due to this part, no? Field is due to this part. Field is due to this part. Field is due to this part, right? And the field here, perpendicular distance r, single-sided. See, to the single side, to a single side of the considered point, single side. Then I over no. Current is capital I, perpendicular distance is r. Then you can keep the final answer as mu naught I over 4 phi r, and its direction is dot. Right? So likewise, two learnings here. One is, if you have a conductor which goes through your considered point, there's no contribution from such conductors because there's no perpendicular distance. Right? That is the first thing. Right? And the next thing is writing the magnitude. Direction is as same as before. And when you are writing the magnitude, you have to pick the correct scenario. Right? We have only 3 scenarios. Out of these 3 scenarios, pick your correct scenario. Right? Pick your correct scenario. Whether it is to a single side or both sides or subtended angles. From that, get the equation and plug it here. Right? Raise your hand if it is clear enough. Raise your hand if it is clear enough. And ask if there's anything. Right? Yeah, it is outwards. No? Outwards. Dot. Aren't dot outwards. That is dot. Right? Outwards means dot. Right? Listen again. We have 2 parts in the given conductor. Right? This one is going through the considered point. This part goes through the considered point. When it goes through considered point, there is no perpendicular distance. Right? We had a perpendicular distance in the equations, no? Right? In the introduction of terms, perpendicular distance or radius. Then here there is no perpendicular distance, not contributing, no contribution, right? But from the other one, there is a perpendicular distance r. To point x, right? And this conductor is only to a single side from point x. Then the equation is I over r. Perpendicular distance is r, so equation is I over r. And for the direction, apply right hand rule for the direction. Now, this is not contributing, only this one is contributing. Then I need direction at point x. Point x is located at the right of this one, that is dot. Right? Clear enough, right? Understand these things from the fundamentals. Then it won't be difficult, right? You will be comfortable with this. That's the thing, right? And always you should be able to imagine and you should be able to argue on these scenarios, right? Okay, then try the second one and send me the answers for second one. Try second one and send me answers. Okay, what are the answers? Right? What about the second one? What about the second one? Direction and magnitude. Direction and magnitude. Second scenario. From here also, one part of the conductor. Now, if it is I, same current flows through this part of the conductor also, no, same I. Right? One part of the conductor goes through considered point. Then no contribution from this part. Right? And this part is a curved part. Then direction at point X is cross. Right? For curved ones, we know our equation is mu naught tau for phi always comes. Mu naught tau for phi always comes. Right? I theta R. Right? I theta R. Then angle subtended here is 180. 180 means 5 radians. Right? Then I theta is phi over I phi over I phi over 5 to 5 cancels. Right? Final answer. Final answer. Right? B is mu naught I over 4R. Direction is cross. Mu naught I over 4R. Direction is cross. Right? Third scenario. Third example. Third example. Now try these ones. Try these ones. This one. this one. Point X is here. And current flow is I. Try this. Third one. What about that scenario? Any answers before I start? Any answers before I start? Now let's try to do this somehow by your own, right? That's the best scenario always, because as I told you, this is actually the unit with the most advanced thinkings we have, right? But we are not going to see, you are not going to see the advanced thinkings just by the first day itself, no? Right? So we are moving there step by step. From the beginning also there are thinkings, but we are moving there step by step, right? Now always when you familiarize these things step by step, right? First stage, second stage, third stage, likewise, then automatically, by the end of the day, ultimately, you will be like mastering this, or you will be fluent in this magnetic fields, right? That is how it should be, right? First day in the fundamentals, fundamentals වලින් තමයි ඔක්කොම ටික වෙන්නේ. Right? This one. Okay. Now, if this current is I, this is I, this is also I. Same current flows through. Right? But this conductor goes through the considered point, right? It goes through its actin line is also going through. That is also enough. Actin line because there is no perpendicular distance, right? 0. 0 means no contribution. Then from these two, there is a contribution from these two. See, now check the directions. There are two now. Check the directions. Because of this linear one, see, cross. Due to the linear one, that is cross. And due to this curved one, see, curved one, apply one. Due to this curved one, that is also cross. Due to both of them, they are cross, no? Then these two are going to add each other. Cross. They are vectors. Then resultant direction is cross. Always mu naught tau 4 pi comes. Right? Then we have two cases now. First one is this linear part, right? X is here, which means this conductor part is only at one side of x, right? IOR. Then due to that one, it should be IOR plus, because both of them create the magnetic field in cross direction. And this one subtends an angle 90 here. This one subtends an angle 90 here, right? Then it goes as I theta r. 90 means 5 over 2 r. Right now, simplify this. Then B equals, right? B equals IOR is common, no? IOR is common. Then mu naught over 4 phi I over R. IOR is common within brackets 1 plus 5 over 2 remains. Right? Final answer is this. Mu naught I, nothing cancels, no? Mu naught I over 4 pi R 1 plus 5 over 2. Right? They are vectors. And if you have multiple quantities, then do a vector simplification. If you have multiple quantities, do a vector simplification. Next. Next. Okay, try this. This one. Try this. No, sorry. Only this part. This one. Try this. Point X is here at the center. Point X is at the center. For that, I got mu naught of 4 half plus 1 over 5. Yeah, it is also correct. You have multiplied the bracket with 5. That's fine. That's fine. If I multiply this 5 into the bracket, the same thing comes now. That is fine. Take a simplification and that's fine. Send your answers. Fourth one. What about this? If you have finished 4, you can try this one also, right? I need answers for question 4 first, right? If 4 is done, you can try this one, 5. If you have finished the 4th one, you can go to 5. What about 4? What about 4? Practice everything by your own, right? After practicing magnetic fields, right, as I told you at the beginning, you are not only going to master magnetic fields, right? But you will be mastering your analytical thinking skills in other questions also, in other units also, like mechanics, oscillations and waves, right? Gravitational fields, thermal, right? All main lessons, properties of matter, right? Because these learnings are, these thinkings are very much handy. They are very much needed, very much handy when it comes to other questions also. Right? They are coming very handy. That's the thing. Since this is the last unit you are learning here as a theory class, as in the theory class, right? After finishing magnetic fields, I'll be starting a question-based revision here on Thursday, right? So I'll be utilizing our theory class time after finishing magnetic fields for the question-based revision, right? So where I'll be revising the lessons again. We will be going through the syllabus again, right? We will be going through the syllabus again, another cycle through the syllabus using questions, question-based revision, right? That's the plan. Or didn't I give the radius? Radius is r, sorry. Radius is r. Radius is r. Okay, see, next one. This part goes through, considered points, considered point, no contribution, right? And this current I flows through this like this, right? Then check the direction of magnetic field at x, right? Due to this curved part, see, due to this curved part, that is cross. Due to the curve, that is cross. And due to this part, linear part, that is also cross. They are going to add up. They are going to add up. Then base mu naught over 4 phi, right? Direction was cross, no? They are going to add up, right? From this one, I theta over r, right? I theta is 3 phi over 2 subtended angle over r plus this is single sided, right? Single sided. single sided, then I over R. Simple I, right? Yeah, simple I over R. Then simplify. I over R is common. I over R is common, so we can take it out. Then mu naught I over 4 phi R within brackets 3 phi over 2 remains here. 3 phi over 2 remains here plus 1. Right? Try this one. 5. Internal radius is simple R, external radius is capital R. Isn't it R squared? What is R squared? I squared. Why? I didn't get your question. Isn't it I squared? What is I squared? You all can start 5. You all can start 5. Right? See, now direction of current is in this part like this, here like this, and here this. These two parts are going through the considered point. Then from these linear parts, no contribution. From these linear parts, no contribution. Right? From the smaller part here, smaller curved part, dot. From the other large part here, cross. Right? We know, lesser the radius, higher the field. Because that is I theta over R. Lesser the radius, higher the field. Then higher field is due to the closer one. Higher field is due to the closer one. The resultant direction is going to be dot. Resultant direction is going to be dot. And resultant is dot B mu naught over 4 pi, right? From the smaller part, I theta over R, then I phi theta is 180 over simple R, right? And from the other one, that is opposite, that is cross minus I phi, same current but different R, I phi over capital R, right? Simplify. I phi is common, so we can take it out. Then mu naught I phi over 4 phi 1 over R minus 1 over R. Right? Then phi cancels. Final answer mu naught I over 4, right, brackets 1 over simple r minus 1 over capital R, right? So likewise, you have to do this vector simplification. They are vectors, right? Magnetic field intensity is a vector. It's a vector. So there is a vector simplification. There is a vector simplification. I have to simplify as vectors. Right. Take it down and ask if any questions. Right. Take it down and ask if any questions. Right. Now this part was about direction and magnitude of magnetic flux density. Right. Before moving on to the next, right, you can quickly go through what we have done from the beginning and ask if any clarifications needed so far. Okay, audit, I have multiple. Okay, right. Anything else? Okay, raise your hand if it is clear enough up to this point. Raise your hand if it is clear enough up to this point. Raise your hand if it is clear enough up to this point. Or you can say it's clear, right? If you are on YouTube, you can't raise your hand, no? Then say it's clear. If you are on YouTube, on Zoom, you can raise your hand, no? Right. So practice these once again and again, and we'll do many practice questions, right? Many practice questions on the next day, right? So as I told you at the beginning, today my main focus is covering these fundamental concepts, right? Fundamental concepts, right? Laying the foundation is the main focus today, right? So you will be learning these things with the foundation, and next week we will be practicing these questions as applications. Okay, right now as a next heading, write down magnetic field of a solenoid. Next heading, magnetic field of a solenoid. Magnetic field of a solenoid. Solenoid. Magnetic field of a solenoid. Magnetic field of a solenoid. Magnetic field of a solenoid. Right. So this is another new part we have to start from here, right? So before starting solenoids, we'll have a break, right? I'm going to give you the break a little bit early today, right? Because I didn't get any time to have my lunch today. After the morning class, I came back and started this one. I didn't get any time to have lunch, right? So we'll be taking the break a little bit earlier today, right? Now it's 5:30 now. We'll be meeting back in 20 minutes, right? Right, let's regroup by 5:50. Okay, we'll start. Right, I'm audible again, right? Right, we'll start. Right, magnetic field of a solenoid. Listen, solenoid. Solenoid means something like this. Now, this is something we make. Right, solenoid එක කියන එක අපි හදා ගන්න ඕනේ. Right, solenoid එක කියන එක හදා ගන්න ඕනේ. Solenoid is something we have to make. Right, we have to make using wires. Usually, copper wires are used for solenoids. Right, so it is something like this. So I think you have seen this. I guess you have seen this. It is like a winding coil like this, right? This is called a solenoid. This is called a solenoid, right? Solenoid, a coil, right? A winding coil, right? When we have to take a wire, make a hadagan easily hadagan puluwa. Take a copper wire and wind this around something, and you can remove the solenoid, and that remaining coil is called solenoid, right? The coil එකට තමයි solenoid එක කියලා කියන්නේ. Remaining coil is called solenoid. And to power up the solenoid, have to connect batteries. To power up the solenoid, we have to connect batteries. To power up the solenoid, we have to connect batteries like this. Right? To power up the solenoid, like this. Right? Now, listen. Now, when the battery is connected, there's a current flow through this. No? When the battery is connected, there's a current flow through this. So we know if there's a single battery here, right? If there's a single battery here, current flows out from the positive terminal, right? Then this is how this current flows, right? See, this is how this current flows, right? මෙහෙම ගිහිල්ලා මේ පැත්තෙන් current flow එක එනවා, like this, right? Now about a solenoid, when we flow a current through a solenoid like this, it creates a magnetic field. It creates a magnetic field in some kind of a different way compared to a single conductor. නිකන් conductor එකේ එන වගේ field එකක් නෙමෙයි එන්නේ. That's why we have to discuss about solenoids as a separate thing. Right? That's why we have to discuss about solenoids as a separate thing. Right? දැන් අනිත් ඒවා අපි right hand rule එක දාලා ගත්තානේ. But here about a solenoid. Solenoid is not just another conductor. There is a special case, a special scenario. Right? In a solenoid, magnetic field is going to be a little bit different. Right? That is what you are going to see here. Right? First thing, when a current flows, ends of solenoid is going to be acting as a south pole and a north pole. Right? Wires are going to be acting as ends of the wire are going to be acting as a south pole and a north pole. Right? This is how south pole and north pole is identified. Listen, if the rotational direction of current is clockwise, right? If the rotational direction of current is clockwise, listen these words very carefully. Listen to these words very carefully. If the direction of rotation of current is clockwise is called a south pole. If the direction of current is anti-clockwise, counterclockwise, that is called a north pole. That is how south poles and north poles are. Identified. Right. Now, when you are checking the direction of current, right, keep your eye outside the solenoid. Now, this is the axis of the solenoid. No, this is the axis of the solenoid. Right. Always when you check the direction of current, keep your eye outside the solenoid. Keep your eye somewhere here outside the solenoid and check this loop. Keep the eye outside the solenoid and check this loop. See, now if you can't imagine it from this 2D diagram here, right? If you can't imagine it by the 2D diagram here, right? Think of a practical scenario like this. Now, this is coming from here, and this wire has wound on this side like this, and this is how the winding is. Right? Ona එහෙම බලලා check කරගන්නත් පුළුවන්. එහෙම බලලා check කරගන්නත් පුළුවන්. See, now the current comes in, is rotating. First loop එක බලන්න, first loop is rotating in this direction. See, this is clockwise. Clockwise, which means since there is clockwise, this pole is a south pole. This pole is a south pole. Right? Now, if you check it from the other side, if this is south, this is definitely north. Right? If there is south, this is definitely north. But to check it, if you check it from the other side, right, what happens is current comes in to the loop by this side first. Right? So solid lines means that is in front of this. Right? Dotted lines means behind the board. Solid means in front of the board. Right? Then current comes into this first and rotated around and goes out. See, anti-clockwise. Anti-clockwise. Right? So likewise, we can identify the poles now, right, of the solenoid. The solenoid is going to generate a special magnetic field. Right? This is a special and a strong one. Nikan conductor ekata meka anith එක strong. Magnetic field of a solenoid is very strong compared to magnetic field of just a conductor. Right. Then we can mark the magnetic field here. Magnetic field lines always go from N to S, no? Right? They go from N to S. They go from N to S. N to S. Then these field lines, if I draw these field lines, right? This is how these field lines go. It is away from N towards S, right? Away from N towards S, right? Then these lines, you can connect them also, right? N to S, like this. And there are infinite number of magnetic field lines here, right? There are infinite number of lines in the three-dimensional manner, right? Simulation I'll show you a simulation also, right? All around, magnetic field is all around. I have drawn the magnetic field on this plane, right? And on the plane also there are like a lot. I have drawn a few, right? Take it down. See, this is what is happening. This is solenoid, and magnetic field is all around the solenoid. Magnetic field is all around. Magnetic field is all around. Right? Magnetic field is all around, and I have drawn a few lines from all. Right? Right? Make it clear. So when the current flows, it generates a magnetic field. Right? It generates a magnetic field when the current flows. Right? South pole and north pole, and a magnetic field. Right? And it is in all 360 directions. Right? That is in all 360 directions. This one is better. Right? So like this, it is in all 360 directions. Right? So I hope you got an idea. That's a thing here. Okay, finish. The identification of south pole and north pole is like this. If the current rotates, if the current rotates in clockwise direction, if the current rotates in clockwise direction, that is a south pole. Right? If the current rotates in anti-clockwise direction, that is a north pole. Right? That is how poles are identified. That is how poles are identified. Right? Right now, listen. For the magnetic field of solenoid, we have a specific equation. Again, we don't have the proof of the equation because again a mathematical part is involved, but we have the equation. Right? So let's assume length of this solenoid as L. Let's assume length of this solenoid as L. Length of the solenoid is L. Right? Then the magnetic field of a solenoid along the axis is given by this equation. Mu naught tau 4 phi always comes. Right? Mu naught tau 4 phi. 4 phi Ni over L, where capital N is number of turns here. Right? Capital N is the number of turns here. Capital N is the number of turns. Right? This is how the equation comes. Mu naught tau 4 phi Ni over L. Right? Now, you can refer this equation either like this. Right? You can refer this equation either like this, or we can cancel 4 phi to 4 phi and we can write the same equation as this also. Right? Mu naught Ni over L. Right? You can keep this in mind in any form. Right? Somehow you have to keep this in mind because this is a direct equation we can use anywhere when we are finding the magnetic field of a solenoid due to solenoid. Right? Write down the equation, then we'll introduce terms. Write down the equation. Before equation, write down. Listen, before equation, write down. If magnetic flux density, write down. If magnetic flux density, if magnetic flux density, if magnetic flux density, if magnetic flux density on the axis of solenoid, on the axis, if magnetic flux density on the axis on the axis of solenoid, on the axis of solenoid is capital B, is capital B, is capital B, is capital B, put a comma and then write down the equations. Right. Right. Okay. Check terms. Check terms. B. Magnetic flux density of solenoid. Magnetic flux density of solenoid. B. Magnetic flux density of solenoid. Right. Then N number of turns. Number of turns slash loops. Number of turns slash loops. Right now in this one, 1, 2, 3, 4, 5, 6, 6 loops are here. Number of turns. Right. I current flows through solenoid. 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 Right. Then L length of solenoid. L length of solenoid. L length of solenoid. Length of solenoid. Right. Now you can see from the equation, right? What can we do if we need to increase magnetic field of a solenoid, right? Number of turns can be increased. Number of turns, right? For the current flow through the solenoid can be increased and length can be decreased, right? Higher number of turns, higher current flow, and lesser length results in a higher magnetic field, right? Next heading. Write down variation of next heading variation of magnetic field intensity. Variation of magnetic field intensity along the axis of a solenoid. Variation of magnetic field intensity along the axis of a solenoid. Variation of magnetic field intensity along the axis of a solenoid. Along the axis of a solenoid. Variation of magnetic field intensity along the axis of a solenoid. Right. See. This is a solenoid now. Right. Should be powered up, right? So it should be powered up. I'm just drawing the variation. Distance and B. Right. So what is happening is something like this. It is a constant along the axis. See, on the axis there is a constant. On the axis there is a constant when n, I, and l are constants. When n, I, and l are constants, there is a constant on the axis, right? Let me draw it here. Then on the axis there is a constant, right? And when we are moving away from the axis, it gradually decreases. Right? When you are moving away from the axis, it gradually decreases. See, then the variation is like this is a constant, right? And when we are moving away, it gradually decreases. Right? When you are moving away, it gradually decreases. Right? This is the variation of magnetic field on a solenoid of a solenoid. Right? For calculations, we will be using only on the axis. Right? Calculations के लिए मैं equation එකෙන් යන දේවල් වලට use කරනවා නම් මේක විතරයි use වෙන්නේ. Right? But when we are moving towards infinity, it decreases from. Right? When we move towards infinity, so that is what is shown here. Right? Take it down. Take it down. I'll explain the variation. And variation means now from the equation here, right? On the axis there is a constant, no, because that is independent of the distance, right? It depends only on number of turns, current, and the length of the solenoid, right? Then on the axis there is a constant, and these two decreases because when we are moving away from the axis, when you are reaching infinity, right? Always with the distance, any field decreases, no. So likewise, similar thing, similar pattern, right? Then when you go to the infinity, it gradually decreases and reaching zero. But otherwise, on the axis, there is a constant according to the equation. Right, finished. Now, using this, let's do a small exercise example. Right, see, example. As an example, write down. As an example, write down. Example, write down. Example, write down. Draw all magnetic field lines. Draw all magnetic field lines. Draw all magnetic field lines in the given system of solenoids below. 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 Right. See. Okay. Try this. First, you can identify NS. Right. First, identify NS poles, and then how to draw magnetic field lines. Is only the coil part called as solenoid. Yes, yes. Right. Only the coil. Right. Coil is a solenoid. Right. Try this one. And please note that these two are different. Right. The winding directions are different. Huh? This winding direction is this, but this winding direction is opposite. This winding direction is opposite. Right. Okay. What about it? First, you identify poles, and then only you can mark or draw the field lines. Right? Identify poles. I have to mark current flows. Now, here current flows out from the battery. Right? Current flows out from the battery. Then, in the first loop, see, current comes into the outer side first and goes down and rotates clockwise. Then this pole is south. This is north. Right? Here, current flows out from this. Current flows out from this. And first it goes to the side behind and comes up. Right? First it goes down from behind. First it goes down from behind. First from behind and comes up. So that is anti-clockwise. N. Right? And S. Right? And here, direction of current is this. Here, it rotates this way. Right? You can check from any direction you prefer. Totally fine. Right? If you need, you can check from here also. Right? Now in this loop, right, it goes up and comes down north, north, south. Right? These are the poles. These are the poles. Right? Then, and other thing, as I told you, when you check poles, always you have to keep your eye away from the axis, out from the axis, and have to check. Right? Otherwise, if you keep your eye somewhere here, it is different. Right? You will see something different. Right? Keep the eye outside to the given solenoid. Keep the eye outside to the given solenoid. Likewise, how to do this. Then N to S, no? N to S. N to S. N to S. Then here there will be repulsions because N and L are repelled away from N. Right? And it is going to connect here to S. Going to connect here to S. Like this. N to S. N to S. Right? And here again N to S of this one. Right? N to S of this one. N to S. N to S. Right? And these two are attracted because they are N and S, then N to S. N to S attracted. And on this on loop, N to S, here N to S, right? And they go out from N, and towards S. Right? So here also these two are connecting back to this one like this. Like this. Right? So before identifying the poles, you can't do anything. Identify poles. Right? If the current rotates clockwise, that is south pole, and clockwise, north pole. And always when you check the directions of current, keep your eye outside the solenoid. Right? And still, if you can't figure it out using this 2D diagram, right? Think of something like this. Pen winding direction. You can check the winding directions on the pen like this and check the direction of rotation. Right? That's a safe approach if you are like not comfortable with the 2D diagram. Right? Complete it. Complete. Okay. Finished? Right, finished. Let's move on. Next. Next. Right, next. Write down the heading. Write down the heading. Force on a conductor. Force on a conductor in a magnetic field. Force on a conductor in a magnetic field. Force on a conductor. Force on a conductor in a magnetic field. Force on a conductor. Force on a conductor in a magnetic field. Force on a conductor in a magnetic field. Right. See. Say we have a conductor like this. Length of the conductor is L. And a current I flows through the conductor. And say a current I flows through the conductor. Right. Listen. Right. And magnetic field acting in this region is, say B, this should be kept in a magnetic field, right? Say we have a magnetic field, cross magnetic field, cross magnetic field throughout this region, right? Throughout the region, we have a cross magnetic field, and the conductor is kept in the magnetic field. Conductor should be kept in the magnetic field, right? Now the field is cross, so that is kept in the magnetic field, right? First thing is about the magnitude, right? Magnitude is given by the equation F equals BIL, right? That is given by the equation F equals BIL. Force on the conductor F equals BIL, right? Where F is the force, B magnetic flux density, I current through the conductor, L is length of conductor, right? And very important, when we apply this equation, it is a must to be B and I perpendicular. It is a must, right? When we apply the equation, B and I must be perpendicular, right? If they are not perpendicular, have to dissolve, right? If they are parallel to each other, no force, because it should be perpendicular, no? If there is parallel means there's no perpendicularity, zero, not even a dissolved component, cos 90 in 0, right? Parallel not should be the perpendicular B and I, right? Take it down first and introduce terms. Introduce terms, take down the equation and introduce terms. I will mention separately about this perpendicularity, right? Write down the equation only and introduce terms. Okay, terms, introduce terms. F, force on conductor, force on conductor, F, force on conductor. B, magnetic flux density, B, magnetic flux density. Now for this purpose, magnetic field should be given separately, because we know in any on field, right, in any field, on field cannot be felt by the on object, no? Now in a gravitational field, we know we can't feel our gravitational field, we don't know, right? My weight is not not felt by is not felt by my system. My system means my body, right? When it comes to electric fields also, own charge cannot be felt its own field. Here also the same thing. Now we know when a current is carried through this conductor, right, through this conductor wire, right, it has its own magnetic field, right, but own field is not felt by that same object. So therefore this external magnetic field is given. Right, මේ තියෙන external එකක් හොඳ. මේ තියෙන external එකක්. මෙයාගේ එක නෙමෙයි. මෙයාගේ එක වෙනස්. මෙයාගේ වෙනස්. This is an external field given. External field. Right? B magnetic flux density within brackets external. Right? Within brackets external. B magnetic flux density within brackets external. External. I current through conductor. I current through conductor. I current through conductor. I current through conductor. L length of conductor. L length of conductor. L length of conductor. L length of conductor. Right? Then write down below with a red pen. Write down below with a red pen. Mention with a red pen. B and I should be B and I should be B and I should be always perpendicular. B and I should be always perpendicular. B and I should be always perpendicular to each other. B and I should be always perpendicular to each other. Perpendicular to each other. When above equation is applied. When above equation is applied. When above equation is applied. B and I should be always perpendicular when above equation is applied. Right? Now you can mention this also. B and I are perpendicular like this. Symbolize it. Symbolize it. B and I should be perpendicular. Right. Now, listen. This is about the magnitude, no? Right? Listen. This is about the magnitude. Magnitude is BIL. Right? Magnitude is BIL. And the other thing is, right? This is a vector, this is force. Other thing is, right? Direction. Right? Other thing is direction. To find direction, again we have another rule, another law. Right? Let's see. As a heading, write down direction of force on a conductor. Next heading, direction of force on a conductor. Direction of force on a conductor. Next heading, direction of force on a conductor. Direction of force on a conductor. Direction of force on a conductor. Right, listen. For that, we have another rule called Fleming's left-hand rule. Fleming's left-hand rule. Right? So what it says is, listen carefully. Right? What it says is, when direction of magnetic field is represented by the index finger. When direction of magnetic field is represented by the index finger, and when the direction of current is represented by the middle finger, thumb gives the direction of force. Right? When direction of magnetic field is given by the index finger, and when the direction of current is represented by the middle finger, direction of thumb gives direction of force. Right? That is called Fleming's left-hand rule. Fleming's left-hand rule. Right? Write down direction of force acting on a conductor kept in a magnetic field. Acting on a conductor acting on a conductor kept in a magnetic field, acting on a conductor kept in a magnetic field, acting on a conductor kept in a magnetic field, conductor kept in a magnetic field, is given by is given by is given by Fleming's left hand rule, is given by Fleming's left hand rule, is given by Fleming's left hand rule, Fleming's left hand, is given by Fleming's left hand rule, Fleming's left hand rule. Right. Now let's see what Fleming's left hand rule is. Write down Fleming's left hand rule. Head in Fleming's left hand rule. Fleming's left hand rule. Right. See. Something like this. Something like this. Fleming's left hand rule means, right, when we keep these three fingers, thumb, index finger, and middle finger, in three perpendicular directions, right? When we represent direction of magnetic flux density by index finger and direction of current by middle finger, direction of force is given by thumb, right? So simply, this is called Fleming's left hand rule. All three are perpendicular to each other. All three are perpendicular to each other. All three are perpendicular to each other, like this, right? Perpendicular to each other, right? Take it down. Right. Write down the law below. Write down the law. Right. Write down the law. Below this one, write down. When thumb, write down. When thumb, index finger, and middle finger. Write down. When thumb, index finger, and middle finger. When thumb, index finger, and middle finger of left hand. When thumb, index finger, and middle finger of left hand are kept in three perpendicular directions. Are kept in three perpendicular directions. Are kept in three perpendicular directions. Three perpendicular directions. If direction of magnetic field, if direction of magnetic field and direction of electric current are represented by index finger and middle finger respectively. By index finger and middle finger respectively. Are represented by index finger and middle finger respectively. Are represented by index finger and middle finger respectively. Direction of thumb gives direction of thumb gives the direction of thumb gives the direction of force. Direction of thumb gives the direction of force. Direction of thumb gives the direction of force. Right. Okay, see, let's see some examples now. Now we know how to write the direction also, right? Let's see some examples. As an example, write down. As example, write down. As example, write down. Find the direction and magnitude of. Write down. Find the direction and magnitude of. Find the direction and magnitude of. Find the direction and magnitude of force on given conductors below. Force on given conductors below. See, first one. Look at the board. This is the conductor. It carries a current I in this direction, and it is kept in a magnetic field cross. It is kept in an external magnetic field cross. It is kept in an external magnetic field cross. Right. So as I told you at the beginning, in the right hand rule also, right? Same things applicable here, right? When you are applying the law, right, always make sure your hand and the diagram are on the same plane, right? See, this is how it is applied. Direction of current. This one, direction of current. Direction of field, cross. Direction of field is cross. Then index finger is cross. Direction of current is rightwards. Then thumb is upwards. Which means direction of force here is upwards. Right? Then you can write the magnitude. F equals BI L. Right? Consider length of the conductor as L. Are you clear about the application? Are you clear about the application? Right? How we apply this? Direction of magnetic field, cross direction of current, rightwards, then direction of force is upwards. Raise your hand if it is clear. If the application is clear, we will practice few examples. Raise your hand if the application is clear. And you can ask if any questions. Right, then try these ones. Starting from the first one. Try these ones. Try these ones. In each scenario, you can consider length of the conductor as L. Right? Okay. Try these scenarios. Try these scenarios. I need direction and magnitude of magnetic field. Sorry, direction and magnitude of force. Right. What about the second one? Right. Look at here again. Second one. Direction of magnetic field outwards. Then index finger should be outwards. And direction of current is upwards. See? Direction of current is upwards. Index finger is outwards. Then the thumb is right. Thumb is rightwards. Direction of magnetic field is outwards. Then apply one outwards. And current is upwards. Then the direction of thumb is rightwards. Force is rightwards. Force on this one is rightwards. Right? Magnitude is F equals BIL. Right? Apply the law accordingly. Right? Just as you applied right hand rule, right? Now we have feminist left hand rule. Feminist left hand rule, right? Then put these three fingers accordingly. Third one. Since this is not perpendicular, you can get the component. This is B sin alpha, right? And this component here is B cos alpha, right? B cos alpha and I are parallel, no? Then no contribution from this B cos alpha. But B sin alpha and I are perpendicular. Then it is going to create a force since they are perpendicular. Since they are perpendicular, right? Apply the law. I is leftwards. I is leftwards. And B is upwards. B is upwards and I is leftwards. And the thumb is now inwards. Right? Thumb is inwards. Then force on this conductor is cross. Force on the conductor is cross. And its value is B is not B, that is B sin alpha. Right? I L. B sin alpha I L. Right. What about first three? Is it clear now? Are you clear about first three? What about first three? Is it clear now? Raise your hand again if it is clear enough now. So far, up to third one. When you apply in the book, that is much easier because either you can either rotate your hand or you can either rotate your book. Right? When it comes to the board, I can't rotate the board. Somehow I need to rotate my hand and apply here. Right? Something like this. But when you are applying on the book, right? If you can't rotate the hand, rotate the book and somehow make sure your hand, your palm and the plane of the diagram are coincided. They should be on the same plane, right? Unless otherwise you are not going to get the correct answer, right? Try the rest now. Try the rest. right? Now always the trick behind this is make sure your hand and the diagram is on the same plane, right? නැත්තම් වැඩේ වැරදි. මේකේ තියෙන එකක් ඔය ඇප්ලයි කරන්න වෙන එකක් නම් හරියට ආන්සර් එකක් එන්නේ නැහැ. මේ තියෙන විදිහට මේක ඇප්ලයි කරන්න ඕනේ. right? එතකොට දැන් මේ අත කරකවන්න බැරි ඩිරෙක්ෂන්ස් තියෙනවනේ දැන්. සමහරලාට මෙහෙම එක එක පැතිවල කරකවන්න බෑනේ. There are some directions that we can't rotate this. Then in such cases you have a book, no? Rotate the book. Right? So that's why I told you always this is going with 3D imagination and 3D setups. Right? That is 3D. 3D. So 2D diagram එක අඳින්න විදියක් නෑ. That is 3D. apply කරද්දි ඉතින් 3D එකත් එක්ක තමයි apply කරන්න ඕනේ. Right? That's easier when you do so. 3D එකම බලන්න. Right. What about 4? 4? What 4 එකට answers ආවනම් කියන්න. What are the answers for 4? Direction and magnitude before I do. What about 4? Anyone? So this is the beauty of magnetic fields, right? Now beauty means some sort of a 3D imagination is there, right? And 3D applications are there, right? මම කිව්වේ magnetic fields වල මේ coplanar forces නැහැ. There are no coplanar forces in magnetic fields, right? coplanar නැහැ. right? 3D ම තමයි යන්නේ. ටිකටම 3D. ටිකටම 3D. Right, see? Now, direction of current is cross. Then, middle finger is cross inwards. Direction of current is cross. And direction of B is rightwards. When apply when no idea. Cross and rightwards, then this is downwards. Thumb is downwards. Both should be on the same plane by the time you apply. Both should be on the same plane by the time you apply. Then thumb is downwards. Then force is downwards. Force on this conductor is downwards. Magnitude is BIL. Magnitude is BIL. Right? හරියටම plane එකේ තියෙන්න ඕනේ. I is cross and B is rightwards. Cross and rightwards. Then thumb is downwards. Thumb is downwards. Correct? Right? ඒ විදියටම apply වෙන්න ඕනේ. දැන් මේ diagram එක මට මේ වෙන පැත්තකින් check කරන්න බෑ. Right? If the diagram is on the board, you have to keep the hand on the board and apply. Otherwise, we can't check it somewhere here like this. Different. That is wrong. That is different. Always you have to stick to this. Right? 5. Try the rest. Right, next one. 5. Direction of current is leftwards and direction of B is also leftwards. They are parallel to each other. If they are parallel, no force, right? Because it's a must to be B and I perpendicular. It's a must to be B and I perpendicular. Then there's no force here. No force. No force. It's a must to be these two perpendicular, right? So when it comes to these forces, this plays a major role in magnetic fields, right? One of the main parts magnetic fields are driven is forces on conductors, right? So මේ part එක හොඳට මේ grab කරගන්න, right? මොකද මේකෙන් තව ඉස්සරහා දිගටම connect වෙනවා. Up until the end of magnetic fields, this is connected now. Right? Forces on magnetic fields, forces on conductors in magnetic fields. Right? What about 6? 6. Direction. Direction එක දාන්න ඕනේ. What about direction? 6. Current is outwards. Current is outwards. And B is upwards. Current is outwards, B is upwards. දාලා බලන්න මෙහෙම තමයි එන්නේ මේ. Make sure these two are on the same plane. See? Current is upwards, current is outwards and B is upwards. This is leftwards. Force is leftwards. Force leftwards. Right? Magnitude is BIL. Right? Seven. 7. What about 7? Direction of current is inwards. Right? And direction of B is this. Right? One thing you need to understand is, even though there is an angle given, I and B are already perpendicular. No? I and B are already perpendicular. Right? I and B are already perpendicular because I is in this Z plane, right? In this Z plane, whereas B is on this XY plane, right? Then when you apply this, current is inwards and B is here, see, direction of force is going to be like this, perpendicular to B. That is going to be like this, perpendicular to B. Right? This is the direction of force. Angle is given just to mislead you. Right? I just gave the angle to mislead you. Otherwise, Z plane to XY plane is always perpendicular. No? Even if you dissolve, right? Even if you dissolve, both B cos theta and B sin theta will be perpendicular to this cross direction. Then again, you are going to write both, no? Right? Same thing comes. F equals BIL. Right? Because this Z axis to XY plane is always perpendicular, whatever the angle it is. Right? One angle එක තිබ්බත් මේ දෙක perpendicular like this. ඔන්න මම මේක පෙන්නන්න. Direction of current is inwards. And direction of B is like this. See? Whatever the angle it takes, it is always perpendicular. That's the thing. Right? Angle is given just to fool you and mislead you. This one. Direction of current outwards and direction of B downwards. Okay? Current is outwards, B is downwards. Right? B downwards, current is outwards, F is rightwards. Right? And the magnitude again is BIL. Right? Check your answers. check your answers and ask if anything to clarify. Ask if anything to clarify, right? Because now about riding forces, it is like the starting part of the core area, right? Core part in magnetic fields. Won't we get the magnitudes in terms of values? Yeah, you will get. You will get. Then if the values are given, then simplify the equation BIL, right? BIL will be given, right? Then simplify, right? Values are there. Values are there. Take down and ask if any questions while taking down. Right. No questions, right? Right. Now today we have covered these areas. See, today we have covered these areas. Started from magnetic flux density, right? We started today from magnetic flux density, right? We started with magnetic flux density. That is also called magnetic field intensity, B, right? So about this we covered two things, right? About magnitude, Biot-Savart law, right? And the direction, right hand rule, and then solenoids, right? About the solenoid, direction of B, then magnitude of B, and the variation, and here about forces, force on conductors, right? Direction is given by Fleming's left hand rule, and magnitude, right? And the magnitude is given by BIL, right? These are the things covered. These are things covered so far, right? Now, probably you are learning these things for the first time, no? Because Fleming's left hand rule is not in O levels, but you have the right hand rule in O levels. But Fleming's left hand rule is not in O levels, right? You have the right hand rule about electromagnetic induction. That is something coming up, right? Now check these things again and again and practice this, because now we are applying hand rules, right? Directions, simplifications, applying hand rules, right? So without being the practice, right? Without having the practice, right? Sometimes you are not comfortable to apply these laws even. That's the thing, because you have to apply this using your hand, using your own hand. You are the one who need to apply, right? සමහර කට්ටියට මේක නිකන් අත මෙහෙම රොටේට් කරන්න කොහොමද කියලා හිතා ගන්න බෑ, right? And මේ පැත්ත රොටේට් කරන්න පුළුවන් කියලා එහෙම දන්නෙත් නෑ සමහර අය, right? Rotate and see whether it's rotatable, right? ඒවා පුරුදු වුණාට පස්සේ apply කරන්න ලේසි, right? Once you get used to these things, right? පොඩ්ඩක් බලන්න ඕනේ. And the next main part we are to start next week. There are two main parts. First one is forces on bent conductors. Now all these were linear conductors, no straight conductors, no. The next part is forces on bent conductors, and the other thing is there is a force movement on a loop in a magnetic field. That is the other main core area here, force movement in a magnetic field, right? There are many beautiful things coming up, right? Because magnetic field is very much different from other two fields, and it has its unique motions on particles, like circular motions, spiral motions, right? Different motions are there. They are unique motions, right? That's a specialty. So as the next heading, keep this written. Next heading, forces on bent conductors. Next heading, forces on bent conductors. Forces on bent conductors. Keep this heading written. So we'll be starting the next day with bent conductors. And other than that, the main part to be covered next day will be force movement on a loop, right? And after that, forces on charges coming up, forces on charges in a magnetic field. These are forces on conductors, no? Then forces on charges in a magnetic field, and then electromagnetic induction. Those are the parts coming up, right? Any questions from the things we covered today? Any questions? Anything to clarify? All clear. We'll be having today there won't be any S2 discussion, right? I'll be allocating it to a different day, right? Now after this class again, I have to go to some preparation for a dancel ceremony. අර dancel දෙනවනේ අපි වෙසක් එකට. මේ ඒකේ පොඩි වැඩ ටිකක් තියෙනවා. ඒ නිසා මට මේ වීක් එකේ මේ questions ටික හදා ගන්නත් time එකක් නැති වුණා. දැන් rare time එකකුත් නෑ. I'll be doing it on a separate day, on a different day. Right? I'll be doing it on a different day. Right? Because this week I thought of discussing structure disease. Right? මට structure ටික හදලා මේ questions ටික finalize කරගන්නත් බැරි වුණා. Because I was full busy throughout the week. Right? Will be free on the Vesak day, right? Now, tomorrow also we'll be having classes from the morning until 1 a.m. right? Starting from 8:30 tomorrow, and 3 classes, and the last class will be finishing at 1 a.m. right? I Saturday තමයි free වෙන්නේ. right? මේ මං S2 එක දාලා කියන්නම්. ඒක Thursday තමයි usually තියෙන්නේ, but today I won't be available, right? We'll do on a different day, right? So kind of hectic these days, right? S2 එක කරනවා, but this week we'll do on a different day, right? I'll inform. You can get all updates from the channel. Any other things? Any other questions? And write all papers without missing anything, right? Now final papers are going on, right? Write all papers, and all ranks of the first paper was given, right? And write all papers, practice more questions, right? And you are writing past papers from the other end, right? So different things, I mean lots of things are happening, lots of different things are happening, right? In other subjects also it might be the same, right? Manage your time and work hard. We are just 11 weeks from the exam, right? 11 weeks from the exam. 11 means now it is actually 10 weeks and 3 days now. 10 weeks and 3 days, right? 11 cannot be 10 weeks and 3 days. All right then, if no questions, we'll wind up, right? We'll wind up. Stay safe and work hard. Now these days again raining and landslide, so some of things are happening, right? Some sort of things are happening around. Stay safe anyway, right? Wherever you live, maybe in a mountainous area, hilly area, right? Or lowland area, wherever you live, be safe, stay safe, and work hard, right? Don't miss your studies, work hard, right? Okay, if any questions or anything to know from my side, feel free to contact me on WhatsApp, right? All right then. Then if no questions, we'll wind up. We'll be spending the coming up 3 to 4 days, right, with magnetic fields, and we are going to finish everything off. And after finishing magnetic fields, as I told you, I'll be starting the question based revision, where you will be going a whole round through the syllabus again, with questions. Right? We'll recall the syllabus again from the beginning using questions, question-based revision. Right? Okay then. Then we'll wind up. Good night. See you in the next class. Goodbye.